Hey there, and welcome. Today we're talking about the hidden architecture of pretty much everything around us, sensors. These little guys are the eyes, ears, and nerves of our technology, and we're going to dive into how they're actually built.
So how does your phone know which way is up? Or how does a smart thermostat know the temperature? It's all thanks to this tiny, brilliantly engineered device, a sensor. But here's the thing, the real magic isn't just that they exist, it's how they're built. The secret to making them work is all about their physical construction.
All right, here's what we've got on tap. We'll kick things off by seeing just how surrounded we are by sensors. Then, we'll basically take one apart, virtually, to see what makes it tick. We'll get into why the right material is the absolute secret sauce, what that even means, and then wrap it all up by seeing how this lets us measure, well, everything.
So yeah, sensors are everywhere. Seriously, just think about it for a second. Your car's parking assist, your smartwatch, your coffee maker, they're all packed with them. And for each one to do its very specific job, whether that's measuring heat or motion or something else, it all boils down to two things: its physical design and the stuff it's made of.
And that brings us to the core idea here, sensor construction. You can think of it as this perfect blend of art and science. The whole point is to build the sensor's body with two really clear goals. First, be super sensitive to the one thing it's supposed to measure. And second, be tough enough to completely ignore all the other background noise and interference. It's all about focus and resilience.
Okay, so what's actually inside one of these things? If we pop the hood, we're going to find four key parts, all working together, each with a super specific job to do.
And I love this breakdown. First up, you've got the sensing element. Just think of this as the sensor's tongue. It's the piece that's actually touching or interacting with the world. Then comes the transduction element, which is like the nerve. Its job is to turn that physical interaction into an electrical signal. After that, you have signal conditioning, which acts as the translator. It takes that messy, raw signal and cleans it up, amplifies it, and makes it useful. And wrapping it all up is the protective housing, the armor that keeps all the delicate bits safe. So tongue, nerve, translator, and armor. Simple, right? But so elegant. All right, so we know the parts, but what are they made of? This is where things get really interesting, because this is absolutely critical. You just can't build a great sensor with the wrong ingredients. The materials, they really are the secret sauce.
And this quote just hits the nail on the head. The way a sensor actually works is completely tied to the physical, electrical, or chemical properties of the material it's built from. The material isn't just some passive box holding the important stuff. It's an active, essential part of the measurement itself.
So what does that mean? Well, it means there's no one-size-fits-all material. It's all about picking the right tool for the job. If you're building a temperature sensor, you need something with high thermal sensitivity, a material that reacts big time and predictably to heat. But for a pressure sensor, totally different story. You might need a material that actually creates a little bit of voltage when you squeeze it, or one that bends in a very precise way.
Which kind of brings us to what you could call the job interview for materials. When an engineer is picking a material for a new sensor, they've got this really specific checklist of qualities they're looking for.
So here's what's on that list. Obviously, it's got to be sensitive to whatever it's measuring. It needs to be stable over time, durable, and resist corrosion. The basics. But these last two are huge for accuracy. You need good repeatability, meaning you get the exact same reading for the exact same input every single time. And you need this other crucial property called low hysteresis.
Now, I know hysteresis sounds super technical, but stick with me. It's basically a material's memory. It's this lag, this delay, and how a material responds when the forces on it change. And for a sensor, that kind of memory is a really, really bad thing. You want it to tell you what's happening right now, not what was happening a split second ago.
Okay, here's the perfect analogy. A material with low hysteresis, it's like a brand new, perfect rubber band. You stretch it out, and when you let go, it snaps back to its exact original shape. Instantly. No sagging, no delay. That's low hysteresis. In the real world, that's why your phone's screen rotates the very instant you turn it sideways. The sensor inside has zero memory of its old position. It just snaps right to the new one.
So when you nail the construction and you pick materials with these incredible properties, well, the impact is just enormous. It has completely changed the game for what we can measure and how we do it.
I mean, the only reason we have these unbelievably tiny and powerful sensors in everything from our phones to life-saving medical gear is because of breakthroughs in material science. Things like advanced semiconductors, specialized ceramics, and even nanomaterials have allowed us to build sensors that are smaller, way more sensitive, and use way less power than we ever could before.
And you see the results of this literally everywhere. Think about industrial automation. These sensors are preventing super costly mistakes on huge assembly lines, or in biomedical devices, where they're true game changers, monitoring vital signs with incredible accuracy. In our cars, they're the backbone of safety systems like airbags and stability control. From the Internet of Things in our homes to monitoring the health of our planet, these advanced sensors are pretty much the foundation of our modern, data-driven world.
Okay, so let's do a quick recap of the big takeaways. First, a sensor isn't just a single thing. It's a whole system of 4 core parts working together. Second, its performance comes down directly to its physical construction. Third, choosing the right material isn't just a small detail, it is everything, and it has to be tailored to the specific job. And finally, for a sensor to be accurate and reliable, you need those key material properties, especially that perfect memory-free snapback of low hysteresis.
And that really brings us to the future, doesn't it? Because the story of sensors is, at its heart, the story of material science. As we keep discovering and inventing new materials with these wild new properties, it just makes you wonder, what's next? What new senses are we going to give our technology? And what will we be able to measure tomorrow that we can't even imagine today?